Hello again. Here's problem number 2, the baseball throw. A baseball is thrown from the outfield toward home plate. The outfielder throws the ball from the warning track, which is about 110 meters away from home. The outfielder's throw is released at a velocity of 35 meters per second at an angle of 25 degrees from the horizontal. Also, the ball is released from the outfielder's hand at a height of 2.3 meters. How far does the ball travel toward home plate before it lands? You'll notice I have made my table already. I would have also drawn the picture in the force diagram, but there are a couple things I want to comment on so you can see while I'm doing it. This throw is going to look very similar to the goal kick, except for that it doesn't start on the ground. It starts from 2.3 meters above the ground, which is where the outfielder's release point is. So make sure you note that on your picture. The ball starts at 2.3 meters from the ground. Everything else is pretty similar to the last problem. The numbers have changed a little bit. The starting velocity is now equal to 35 meters per second. A baseball can be thrown a little bit faster than a soccer ball can be kicked. And the angle of it is 25 degrees from the horizontal. But other than that, this problem is very similar to the last one. We have, once again, gravity acting on the ball, but no other forces, at least none that are important. Probably drag force actually is at least a part of this problem, but we don't have the tools to analyze drag force yet, so we'll leave it out. Now let's fill in our table. The mass was given, 0.15 kilograms. We don't know the time that the ball took to reach its landing spot, but we do know the ball's starting position. We can set the 0 in the x direction to be right where the ball starts. We want to set the 0 for the y. We could set it to be anything, but it usually makes sense to set the 0 at the ground. So we'll set the 0 at the ground, meaning that the ball returns to the ground. The final position will be 0 meters, but the starting y position will be 2.3 meters above the ground. The final position is unknown. The starting and final velocities are also unknown, but we can get those fairly easily, like we did in the last example. And the accelerations are also known. There's no force in the x direction, so the x acceleration, 0 meters per second squared. There's only gravity force in the y direction, so the y acceleration is 9.81 meters per second squared in the negative direction. Now let's go ahead and get those velocity components. Ooh, went too far. All right. We'll break our original velocity into its components. "35 meters per second original velocity, and the throw is 25 degrees from the horizontal, which allows us to do, once again, fairly simple trigonometric calculations and find that the starting x velocity is equal to 31.72 meters per second, while the starting y velocity is equal to 14.79 meters per second. So I'll fill those in the chart. Now, once again, we are looking for how far did the ball travel before it landed. So that is a final position kind of question. In order to get that final x position, we're going to need to use equations, and we need to know which ones we're allowed to use. In the x direction, we've got constant velocity because the acceleration is 0 in the x direction. So we're allowed to use constant velocity equations in the x direction. In the y direction, we've got constant acceleration because there's a constant net force in the y direction. Specifically, it's provided by gravity force, which stays constant on this ball. Constant acceleration in the y direction allows us to use constant acceleration equations in the y direction. All right, that sets us up. We're allowed to use constant velocity equations in x direction, constant acceleration equations in the y direction. I'll go on to page 2. Just like last time, we're going to need to know the time the ball was in the air in order to find how far it went, but we don't know that time yet. So we're going to use the y position equation to tell us how long the ball was in the air. This is going to be a common technique because the thing that determines how long the ball stays in the air is, well, how fast did the guy throw it up? If he threw it almost straight up, then it's going to stay up in the air a lot longer than if he had thrown it more horizontally, like in this case. On the other hand, if he throws it not very fast, he might have thrown it straight up, but if it's not very fast, then it won't stay up in the air very long. So it's this initial y velocity that determines how long the ball stays in the air. So let's fill in what we know. The final position is 0 meters, but the starting position in this case is 2.3 meters above the ground. Starting velocity is 14.79 meters per second in the y direction. And the acceleration, once again, is negative 9.81 meters per second squared. So I filled in the values I know. I will rearrange this equation to set it up to do a quadratic formula on it. Once again, I'm simplifying that lead term. We want to get this into form where the lead term is the t squared term, the second term is the t term, and the last term is what's called the constant term, meaning it doesn't depend on t. So now that it's in that form, I can see once again this thing is A. I'm labeling them. This one is B. This one is C. And I can now use my quadratic formula to solve for what the unknown delta t is. Delta t equals negative b plus or minus the square root of b squared minus 4ac. And all of that is divided by 2a. Note the a is, in this case, is just a label. It's not the acceleration. It's just a label for the quadratic formula. All right, I plug in some values. Once again, I will get two possible solutions, and you need to decide which one is the real solution. It should be pretty obvious which is the real solution. For example, in this one, we're solving for a length of time, and if we get a negative time or a 0 time, we know that that is not the reasonable solution. We're looking for a positive time that would indicate about how long the ball stayed in the air. So we'll guess the ball is going to be in the air for a few seconds, not very long. Once again, I will always give you reasonable numbers for your problems, so you should get reasonable answers. And now that I have filled in the numbers I know, I plug them into my calculator and solve for the length of time the ball is in the air. So at this point, you should pause the video, go solve it for yourself, see what you get. And when you've got a solution that makes sense, come back and see if you're right. I find that delta t equals 164 seconds, which seems about right for the length of time a baseball throw is in the air. Maybe a little bit long, but it's at least the right order of magnitude. I can plug that back into my constant velocity equation that will tell me what the final x position of this ball is. My x velocity was 31.72. Excuse me. Cord fell out for a moment. 3.164 seconds. And the starting x position was 0 meters. I run that in my calculator, and I find that the final x position is 100.36 meters. This would be a phenomenal baseball throw. It's certainly a reasonable answer, but 100 meters is the length of a football field. So that's probably a little bit long, probably a little bit unreasonable. And the reason that it's a little bit unreasonable is because we've, once again, remember, neglected drag force, which slows the ball down. A baseball player throwing a ball at what did we say he threw it at? 35 meters per second. That's about 80 miles an hour. The drag force is definitely acting on this ball, which would make the real length of the throw a little bit shorter than that. But for our more ideal situation, this is about right. Okay, I'll see you in class.